Let us now look at time-dependent problems. An example of such problems arise in thermal physics, for example, something we have already looked at briefly, is the heat equation. And the three-dimensional version of the heat equation is shown here. You have a derivative of temperature with time on the left-hand side. And on the right-hand side, you have a second-order special derivative of temperature, the Laplacian of the temperature. And there is a coefficient of thermal expansion that appears in front of this in front of the Laplacian, and you can have a source term which is like a heat generation rate. For example, if you are holding a flame or a heater towards one end of a wire, that is acting like a source term that's supplying heat at a particular rate to the wire, shown here, for example. And so let us now try to simplify this and look at a simplified version of this case. So the important thing to note is that there's a temporal derivative, temperature is varying with time, and there's a spatial derivative, temperature is varying in space also. And one special case of this is the steady state case, which means the gradient of the temporal gradient is zero. That means del T, the derivative of temperature with respect to time is zero. That is a special case called the steady state case. I just wanted to mention it, but we won't be looking at that case here. We will be solving at the time dependent case. And to simplify the heat equation, we will make a couple of assumptions. First, let us solve in one dimension, and let us assume the source term, the heat generation term, is zero. Then the equation becomes very simple. It is just shown here. Delta of temperature over time, delta time equals alpha times the second derivative of temperature with respect to x position. And now my solution for temperature will be in terms of two variables, time and space, position. And the space part, I can solve it as before. I need a special I need a spatial domain where I will discretize it into a set of points, and then I will use the finite difference technique, and I will also apply the boundary conditions, because this is a boundary value problem. I have to set temperature to certain values at some points in space. For the temporal part, the time dependent part, it will be solved by time stepping. We will take small increments in time, delta t, and solve the equation and see how the solution evolves in time. And to do that, we need some initial condition at the start, in this case t equal to 0. We need to know the form of the solution at the start. So the temporal gradient is defined as this. So we have two time steps, ti plus 1 and ti. They differ by a time step of delta t, and the first order gradient you can just calculate like this: the difference of the two temperatures at the two instances of time divided by the time interval. And this variable is defined at each position xj. And then for the spatial part, we solve it as before. So we have a set of points, and we can define the second derivative as we have done in the previous lectures to solve the Poisson equation. And this is valid at one particular instance of time, ti. Now the total equation looks like this. And now you can solve for the time step ti plus 1 by rearranging the equation. Put all the time steps that involve ti to the right hand side, and the equation becomes like this. So if you know the solution at some time step ti, you can find the solution at the next time step ti plus 1. To demonstrate this on a simple problem, let us try to solve this problem for a special domain consisting of 3 points x1, x2, and x3, and let us solve this for two time steps t1 and t2 at two instances. And we will need some initial condition at the start, what is the solution, and we need some boundary condition, that is the temperature at some specific nodes in the spatial domain. In this case, we add the extra nodes x0 and x4 as the boundary conditions as before. So this discretization is shown at the start t0, and now the temperature is a function of both variables, temperature time and position x. And now we set the boundary condition that the temperature is 0 outside this domain at the edges of the domain. And then from this equation here on the right hand side, you can solve the solution for the next time step t1. And this the value of the temperature at each of the positions will change at this from beginning basically. So this is called time evolution. And we can also write this in matrix form. So this equation and the matrix forms looks something like this. So on the right hand side, this 3 by 3 matrix is again the Laplacian operator, and then I have the temperature at t0. It has three values because I am defining it over the three positions. And then I have the special the starting temperature and then the final temperature at each of the positions. So this is the same equation as this, but represented in matrix form. And notice this factor alpha delta t over a square. A is the special discretization step, distance between the 2 points x1 and x2, and delta t is the time step. And once I know the solution at t1, I can do the same procedure and arrive at the solution at t2, the next instant of time. And one thing to note is that, so this is called forward stepping, right? So I am going forward in time in the solution from t1 to t2. And sometimes this is unstable. So this approach works better if the time step is very small. Actually, to be more particular, this variable, this quantity alpha delta t over a square is much less than 1. So that means the time, basically the time step is much smaller than the spatial step basically, and it's multiplied by, also it depends on this coefficient alpha, of course. So to improve convergence, because the previous solution was sometimes unstable and has some convergence issues, to improve the solution, sometimes another approach is used. It's called Crank-Nicolson method. So again, we have the same equation we showed earlier. This has a first order derivative in time on the left hand side. But in the Crank-Nicolson method, what we use is that we just don't use one time step, but we also look at the solution at the next time step. So for the spatial gradient on the right hand side, we were evaluating it at one time step ti, but now we also add this spatial gradient at the next time step, that is what is the value at ti plus 1, and then we take the average of the two between the two spatial derivatives for the two time instances. We average them and add them here. I have highlighted the new part in red here. And then I can rearrange all the terms involving time step ti plus 1, bring all of them to the left side, and I can bring all the time steps involving ti to the right side, and then I end up with an equation like this. And notice this factor. So this is by multiplying both sides by delta t basically, and factoring out the delta x's. So I call this factor r. And then the new equation looks something like this. On the left hand side I have all the temperature terms at the instant of time ti plus 1, and on the right hand side I have the temperature terms at the instant ti. And I can again write this in matrix format. Now the matrix looks something like this. On the left hand side I have this matrix, and on the right side I have another matrix on this form. And then these are the temperature, the solutions for the temperature at the instant ti plus 1 at the instant ti. This is what I need to solve for, ti plus 1. And there are many ways to solve this. The common way you would think is to do a matrix inversion. So you invert this matrix and multiply by the inverted matrix on both sides, and then you can end up with this. But that's actually not an efficient solution. It may work well for very small system like a 3x3 system like this, but when the matrix is large, matrix inversion is actually a very time consuming problem. And in all the computational problems that you solve, it is better to avoid matrix inversions. Fortunately for tridiagonal matrix inversion, there are some specific algorithms. One such algorithm is called the Thomas algorithm, or the tridiagonal algorithm. Here's a link that will show you how this algorithm works. So this is based on the exact format of this tridiagonal matrix, and it avoids a full matrix inversion, and that is very efficient when you are solving tridiagonal systems such as this. And in many problems you will encounter tridiagonal system or block tridiagonal system, and so it's good to use an algorithm such as this. So why do we need Crank-Nicolson? Because Crank-Nicolson method is second order in time. So initially in the previous method, the brute force approach, we were just our solution was accurate up to first order in time. But the Crank-Nicolson method is actually second order in time, so sometimes it is more stable as such. Okay, so now let us look at another problem, a very important problem from electromagnetism. Is the Maxwell's equations. And you are those of you who have taken electrostatics, you have seen Maxwell's equations before. Two equations are shown here. One for the electric field, the other for the magnetic field. And the curl of the electric field is equal to the temporal derivative of the magnetic field. And the curl of the H field is equal to the temporal derivative of the displacement, electric displacement plus the current density J. And the relationship between B and H, as you know, is related by this mu, magnetic susceptibility, and D, the displacement field, is related to the actual electric field by the epsilon, the dielectric constant. So you can substitute this in the equations and write everything in terms of E and B for example, and solve this. And just for your reference, the curl is defined as this, as the determinant of this matrix. But you notice that the solution of this problem is a bit complicated, right? Because you have to solve for three components, and you have spatial derivatives as well as time derivatives. And also the solution of one depends on the solution of the other. So these are actually coupled equations. You have to solve them self-consistently. Now let us look at a special case and apply and combine our knowledge, what we have seen before in terms of finite difference and time-dependent problems. So this is a method called the finite difference time domain, FDTD. And this is very commonly used in electromagnetics. And let us again simplify our problem a lot, so that it is easier to follow, because this is a complicated problem involving uh, uh, like three components of a vector and uh, and many variables basically. So let us simplify this by assuming that the electric field only has a x component and the magnetic field only has a y component, and the current density, let us assume that to be 0. Then for the electric field, we can write an equation like this from the Maxwell's equation. I have just evaluated the curl and set the y and the z component of E to be 0, and I end up with an equation like this. And from Maxwell's equation, from the first equation here, I can also write this in write the right hand side of this equation, which involves time derivative of b. And now I have two components, j and k, and I can equate each of these components separately, right? So I end up with these equations. And notice that the bz is 0, which I have already assumed in the problem. So I can ignore even the k derivative here, the time derivative in the k direction. And the two equations I have are the following. Equating the components of the j vector, I have del Ex over del Z equals del By over del T. And the other equation is simply del Ex over del Y, negative of that, equals 0, because I don't have the k component on the right side. Now for the other equation, del cross H, the curl of H, I can write H in terms of B. I'll have an extra factor of mu, but I can evaluate this. And again, the magnetic field has just one component, so I can simplify the curl. It has now an I and a k component. And now on the right hand side, I can, instead of D, I can substitute the electric field, because they are related by epsilon, and I have this additional factor mu over epsilon, and I have the two components. Notice again, del Ez, del T is 0, because that is what I assumed in the problem. So again, I have two equations. The first one gives me minus delta By over delta Z equals mu over epsilon delta Ex over delta T. And the second one is simply the k component is 0. Now I can again solve this by assuming a simple spatial grid, but notice that now my both the Ex and the By component, they are varying in the Z direction basically, as shown in this derivative. So I will discretize my space in the Z direction basically. Let us choose 3 points, Z1, Z1, Z2 and Z3, and we need to evaluate these components. The X component of the electric field at each of these 3 points, and also the Y component of the B field in these 3 points. And again, for the spatial part, we need to insert some boundary conditions. So let us put these additional nodes in the solution, Z0 and Z4. And notice time is also a variable in this factor, because I have a temporal derivative on the right hand side of these two equations. So this solution, I have represented it as just one instant of time. But once you obtain the solution, you will get the general solution, which is a function of time, which evolves in time basically. So one thing to note is that these two equations are also coupled differential equations. If you start with an Ex field, that gives you a By field, and then again you have to put the By field in the left equation, and then that will give you an Ex field again, and the Ex field you have to plug back into the right equation again. So you have, these are coupled differential equations, if you remember from the example I have shown in the previous lectures. And so you have to solve them iteratively or self-consistently till both the components converge. And I have already talked about boundary conditions. You need boundary conditions on Ex and By. And you also need some initial conditions, because this is a time-dependent problem. You need some initial conditions on these solutions as well. So these are coupled differential equations you solve by iteration. And the temporal gradient I can calculate as before, taking a small time step delta t and evaluating by at two instances of time. Similarly, uh, I can calculate the temporal gradient of ex, the time derivative, in a similar way. And for the special derivative, as I have shown before, I take a grid of points and use finite difference techniques. And the first order finite difference, I use the first order finite difference equation for the derivative for the points z1 and z2, and I can do the same for z2, z3. These are basically just the differences between the two quantities at the 2 points and divided by their separation. In this case, it is the variable a. So this is finite difference, and the time stepping is called actually the finite difference. The special difference is called forward difference because I am going from z1 to z2 to z3 basically. This is forward different. This is difference. This is also forward in time basically because from ti step I am going to ti plus 1. It is also possible to do backward stepping, but let us do forward time stepping. And notice that only first order derivatives are involved and we are just using two adjacent points. So actually this is kind of limited, kind of a limited approach. It's kind of error prone because it's only accurate up to first order, and also sometimes it's unstable. So it has got stability and error issues. And one way to improve the solutions for some problems is to take a central difference in the special derivative. And what I mean by central derivative is shown in this figure. So if I have two adjacent points along the curve, I can take a forward difference when calculating the derivative. So for example, my value at this point minus my value at this point divided by the by the difference delta x or h, that will give me a forward difference. Or I can do the backward difference. So I am interested in the value of the derivative at the top of the curve here, and I can use that point and the point one step backward here. So this is called backward difference, shown by the green line, and the forward difference is shown by the blue line. Also, I can do a central difference, which is basically I take the backward, the point that was one step back and the point that was one step forward, these two, and I can evaluate the derivative by subtracting the functions at these two grid points. And then the special step delta x is actually 2h here. So that is actually better because you see that, I mean, if you take the slope at the top point of this curve, that slope is closer to the red line, right? But that slope is nowhere close to the blue or the green line. So this actually improves the accuracy in the central difference approach. And in the forward difference approach, what we have used, the error is of the is a first order. And then if you take the central difference, error goes as h square, so it's the second order. So there's an improvement. And so there are many subtleties in this. So this is a very matured field in electromagnetics, numerical electromagnetics. People have many different types of approaches to solve Maxwell's equations. But in the simplest case, this is an approach to analyze electromagnetic fields. And to summarize, so we have looked at time-dependent problems, how to solve them through time stepping. And the features of a time-dependent problem are the initial conditions and time stepping. You can use forward time derivatives, for example. We have looked at at a simple case of the heat equation to show how this works. We have looked at conditions for stability and error. We have also looked at the Crank-Nicolson method, which is an improvement over the first order forward time derivative. And then we have looked at an instance of Maxwell's equation and how to use the finite difference time domain method to solve this problem.